So in today's lecture, I want to talk about the phase diagram of vortex matter. So the picture that I want you to be thinking about is that I start off with some degrees of freedom, which in this case are helium atoms. And then these things undergo some form of off-diagonal long-range order through some kind of superfluid transition. And, and once I've got that off-diagonal long-range order, then in that order, I can find topological defects. And those topological defects have interactions in just the same way that the original degrees of freedom had interactions. So I can call these interacting degrees of freedom, and I can call these interacting topological defects. And once I have these interacting topological defects, then they can undergo a sequence of phase transitions in general. And in particular, because they are interacting, they can form a state whereby they have some form of long-range order. And so those topological defects, because they're interacting, what they try to do is they try to minimize their energy. And so they form a state of long-range order, and we'll see that that is a vortex lattice. And once I've got a state with long-range order, then of course that state can also have its own topological defects. So that would be, in this particular case over here, the long-range order here for line defects would be a vortex crystal. And then the topological defects that you would get in the vortex crystal would be dislocations in the vortex crystal. And of course, dislocations also interact. So these are, in fact, interacting. Whoops, wrong color. So these dislocations can then order to form new states of matter. So these can also order. And this process goes on forever. Okay, so it's a very interesting picture that we can have of what constitutes matter. And so in today's lecture, what we're going to be looking at is so there's, let's just say that there's a hierarchy of types of what we can just call matter. And in today's lecture, we're going to look at the phase diagram of vortex matter. So let's talk about what is section part 4 of the current chapter in my notes, and this is called the onset of vortex creation. So what we're going to start off by considering is a superfluid that is slowly rotating. So we saw last time that a quantum vortex line had has energy. So the basic idea is this, that we start off with a slowly rotating superfluid. And because it is slowly rotating, what that means is it doesn't have enough energy to create a quantum vortex line. And then what we're going to do is we're going to increase the rotation rate. And see what states emerge. So let's calculate the critical angular velocity. So what is our goal? Our goal is to calculate the critical angular velocity where a quantum vortex line first appears. So that's really just a question of energetics. So what we're going to do, the way we're going to do this is by transforming between a frame that is in the laboratory and a frame that is co-rotating with the fluid. So the first thing is that we use some kinematics. So our kinematics says that if I have a rotating frame with some angular velocity capital omega, then the energy in that frame is the energy in the inertial frame, the laboratory frame, minus the angular momentum dotted with the rotation vector. So that's just kinematics. So let's suppose now that there's no vortices. And so that means that the helium-2 superfluid component is stationary. And then we want to ask, well, what is the energy difference between a state with one vortex and a state with no vortices? And then what we're going to ask is that energy difference positive? So the strategy that we're going to undertake is compute the energy difference between this state and a state with one vortex. So what we'll do is we'll call that energy delta E, and that's going to be the energy when I have one vortex minus the energy when I have no vortices. And from the formula up here, this is the same thing as the energy of having a vortex, which has an angular momentum minus omega times the angular momentum of a vortex. And the state with zero vortices gives you nothing to that. So now we can use the results that we derived last lecture. So we calculated the energy of the vortex and we calculated its angular momentum. So I'm just going to plug in the formula that we calculated last time. So of course this delta E is proportional to the length of the bucket, so the height of the vortices. And then the term that comes next is just the energy, which was logarithmically divergent. and then the angular momentum, which is omega, and then the angular momentum was just pi rho s h bar over m times r squared. And so I can write this in the following way. I can write this as some stuff times so you can see here that there is a term which is the angular velocity, which is the thing that we are interested in, and then there's a term that doesn't depend on that. So I'm going to write this in the following way. I'm going to write this as some quantity, which I'm going to call omega c1 minus omega. And then the thing that is going to come out in front of these things is just this prefactor L times pi rho s h bar squared over m squared r squared, like so. And then from this formula, I can then simply read off that means that omega c1 must be equal to h bar over m r squared times the logarithm of r over r naught. So this simple calculation then tells you that that when the delta E is negative, then it is energetically favorable to create a quantum vortex. And what is that? What is that quantum vortex? You know, what is going to happen? So we only know it's energetically favorable. We're not going to talk about the kinetics of that. But what will happen is the system can lower its energy and create the quantum vortex. And so what you end up with is a n equals 1 vortex at the center of the bucket. And if we ask what is the numerical value for this, so let's suppose we take the radius of the bucket as being 1 centimeter, we take r naught is about an angstrom, then that gives you, just plugging in the formulas, 2 pi over omega c1, so that's the period, that's about 35 minutes. Which is quite slow. So that's how the vortex gets created. Now, what happens as we increase the angular velocity? So as we increase omega above this critical value, which I've called omega c1, then what of course happens is you get more and more vortices are generated. Because the vortex at the center then becomes unstable and wants to create smaller charge vortices. The vortices repel, and we saw that last time due to their interactions. And so what happens is then to minimize their energy, they form some kind of vortex lattice. And that spaces them out evenly. And of course, you know, that's going to be very close to the center of the bucket. If you took into account the actual, you know, radius, then in principle there would be a slightly spatially varying lattice constant, but we're going to ignore that. So you're going to get more and more vortices created in a bigger and bigger vortex lattice. Okay, so that's how they're created. Now, how about how they get destroyed? So now this is the destruction of the superfluid state. So let's think about what must happen. So as we increase omega further, then eventually we get so many vortices that they start to push into each other. Because they're in a finite size box, and eventually that means that their cores will eventually overlap. And ultimately, there will be essentially no superfluid left. And so what our question for now is what is this critical rotation? So let's calculate that, and the way we're going to do it is we're going to calculate the number of vortices per unit area, and then we can find the mean separation between vortices, and then we can see when that mean separation is of order the core size. So the answer to our question is we're going to calculate the number of vortices per unit area, and then we're going to, and from that we can then find the mean separation. And all of this is a function of omega. And then when that mean separation is of order the core size, then we will have we'll find this critical omega. And then what we'll say is when the mean separation is of order the core size, and that will give us our critical omega, and I'm going to call that omega C2 as opposed to omega C1 that we had before. So let's go ahead now and do this calculation. So the way we're going to do that is I'm going to assume that what we have is NV vortices per unit area. So then I want to know, well, if I have these vortices, they're going to simulate a solid body rotation. So let's work out what that rigid body is going to effectively be rotating like. So what I'm going to assume then is I have a picture like this. So looking down at my bucket from above. So this is the center of the bucket. This is the radius of the bucket, and then at some distance r, we'll call this little r. I have some curve like this, and I'm going to compute the average velocity at that distance r. So I've got a bunch of vortices in here, which I'm not drawing, and we're going to find out what is the effective velocity for those vortices. So let's write it down like this. So I'm going to say that the average velocity at some radius r, that's just going to be 1 over 2 pi r times the line integral around my curve C of dr dotted with v of r. So that's how I can define my sort of average velocity. And then I can calculate this because I know that I've got NV vortices per unit area. So inside this shaded region, I know how many vortices I have. So I can write this whole formula down as 1 over 2 pi r, and then it's going to be the number of vortices contained within the curve C times the quantum of circulation, which is 2 pi h bar over m, like so. And then this thing is just 1 over 2 pi r times 2 pi h bar over m, and the number of vortices in the curve C is the number of vortices per unit area, NV, times the area of that shaded region, which is pi r squared, like so. And so what I get then is that this average velocity is just pi times h bar NV r over
I'm sorry.
Wait 1 second, please. And that is just, oh, the writing disappears. Okay, let's see what happens. I got pushed off. Thanks for letting me know. How did that happen?
It's been happening a bit in other lectures too. It might just be a Zoom thing.
Don't know. Okay. All right. When did that start? Was it just when somebody interrupted me?
2 minutes ago, maybe.
Oh, tell me as soon as it happens, okay? Because when I'm writing down here, I don't see what's on the screen. Okay. Okay. How far back do I need to explain?
I think right after the number of vortices in C, I think was the point. We never know if it's lagging or if it's actually like not showing up for everyone. So we sometimes wait.
Yeah, no. I think what happened was I got a message over some messaging app and it just somehow kicked me off. So apologies about that. Okay, so all right, let me try to explain again. So I'm calculating the average velocity at some radius r due to a whole bunch of vortices that are stuck inside this sort of gray area in here like this, and so I define that to be, I know that if I have some average velocity at r, then 2 pi r times that velocity is just going to be the same thing as this line integral of the actual velocity, and then I'm going to compute that by just counting how many vortices are contained within the curve and multiply that circulation by the quantum of circulation that each vortex has. And so that then gives me 1 over 2 pi r times the number of vortices there, and the number of vortices that are in the contained within this curve is just the area times the number of vortices per unit area. So that's NV pi r squared. And then I just have this the other factors in front. And so that just simply gives me the formula that I ended up with.
Can I ask a question? So Is that integral a line integral or area integral? Sorry, because you eventually count the vortices inside the area. So I'm wondering, the first equation, is that a line integral or area integral?
It's a line. It's a line integral. I'm computing the circulation.
Okay.
Okay, so once I've got this, then I can say, so now I've got the average velocity as radius r is proportional to r, just as if I had some rigid body rotation. So this thing here is like rigid body rotation. And so I can define this thing to be I can just define this to be some effective omega times r. So if I had a rigid body rotation, the velocity is omega times r. And so what we can see then is that the effective omega is equal to pi h bar times the number of vortices over m. Okay, so that's the effective rotation rate of a bunch of vortices. Okay, so now the question we have to ask is, well, how does that help us find the critical omega? So what we know is that when this isn't this is not the same thing. This is not the actual omega. It's just the effective omega for a bunch of vortices, but it is equal to the effective omega when all the vortices essentially have gone, the cores are overlapping, and all I've got left is normal fluid. So this is not this in general, but for omega equals the critical omega, omega c, then omega effective does equal the actual omega, because then we've just got a bunch of essentially normal fluid. So what is the criterion for the destruction of superfluidity? So that is when the distance is of order the core size. So what is the average distance between vortices? Well, how do we get that? Well, we know that there are NV vortices per unit area. And so that means that the area per vortex is NV to the -1, and that means that the length per vortex is NV to the -1/2. So therefore, my criterion is that is that what I need then is superfluidity gets destroyed when the vortices are separated by something like the vortex core size. So that means, in other words, NV to the -1/2 is of order R0. Okay, well, why is this helpful? Well, we know that the effective omega depends on NV. Okay, so here is NV over here. That defines this omega effective, and this omega effective is equal to omega when we're at this upper critical rotation rate. So I can replace NV by a formula that involves the critical rotation rate. So let's just go ahead and do that. So what that says is then that pi h bar over m omega c2 to the 1/2, that thing is of order the core size. And so modulo factors of pi and things like this, what that then tells us is that omega c2 scales like pi h bar over m r naught squared. And so that's some quantity that's of order 10 to the 12 per second, a rotation rate that's incredibly fast. So that's our final result. So let's now summarize these calculations and sort of sketch what the phase diagram looks like. So let's write it down in this way. So comments. So the first comment is when omega is greater than this omega c2, the fluid is essentially like a normal fluid. And rotates with omega effective exactly equal to the actual rotation rate that you're spinning everything at. What about when we're not in that regime? So we know that we need to have vortex matter. We have to be above the omega c1. So now we have omega less than omega c1 less than omega c2. So in this regime, in this regime over here, then what happens is the effective omega is less than the rotation rate of the bucket. It's not exactly rotating with full rotation, and this is controlled by how many vortices you have. And that number, of course, increases as I increase the omega. So what we can do is we can work out a kind of a moment of inertia of the superfluid. So we can express this in terms of a moment of inertia. So how do we do that? Well, I'm just going to sort of write down the formula. It uses a result that you have in the homework. So the angular momentum of the superfluid component is going to be this. So what we're going to do is we're going to write down the angular momentum of all the vortices. We know how many there are per unit volume, and so we're going to just integrate over those. So let me write it down like this. So there's an L here, which is the height of the bucket. It's not angular momentum. Integrate over to a radius r over the cross-sectional area, so we'll call that RV, which is the summing over all the vortices. The number of vortices per unit area is NV. The angular momentum of each vortex is h bar over m times pi, and then what comes in here is r squared minus the position of the vortices squared. So this is the angular momentum of a vortex at a distance r from the origin. So this is something that you're trying to compute in the homework. and then we just add that up over all the vortices. So so we get something like this, and then this angular momentum, well, the way we define a moment of inertia is that this thing should be equal to the height of the bucket, again, just to make sure everybody is on the same page here. So we have a bucket of size L rotating omega like this. So this is L times the sort of classical moment of inertia times omega effective, and this I classical is just the integral of rho s r squared d to r over the area of the bucket, and this you can just work out is rho s times pi r to the fourth over 2. So that's the classical moment of inertia, and so we essentially have a kind of classical rotating fluid, but the angular momentum does not quite follow that of a regular classical fluid. So let me show you exactly what we mean by that. So here's the rotation rate, and here is the total angular momentum. So this is LZ, and then I'm going to draw on here the critical omega 1 and the critical omega 2. So what is this? What have we just computed? So what we just computed was that at very high rotation rates above here, then above my point here, what's happening then is that the fluid is literally rotating like a classical normal fluid. So in that case, L would be directly proportional to omega. So if I draw a straight line going through this point here, then this curve is going like that. And then we also know that below, let's use a different color so we can actually see it more clearly, below omega critical 1, there is actually no rotation whatsoever, and then in between it has to sort of come up gradually like that. And so the fluid rotates not quite the same as if it were normal, but at least rotating with some effective moment of inertia. And we can write this as a kind of phase diagram. So if I go back and draw down here, so here are these two critical velocities. We can draw the phase diagram, and on the vertical axis, why don't we plot the moment of inertia, which is the total angular momentum divided by omega. So then what do we have in this phase diagram? Well, down here we have no vortices whatsoever. In this regime over here, it's essentially normal fluid. It's essentially just regular matter. And then in between here, we have a vortex array in the superfluid. And so we can think of this as being a vortex crystal. So this is then the phase diagram of vortex matter, at least in this simple in this simple case of a superfluid. Now, I should tell you that what we just calculated was very elementary, just to sort of show you the most basic ideas. But the same kind of calculation applies equally well to helium-3, where you have many more complicated topological defects. It happens in superconductors, where you have what's called the Abrikosov vortex lattice. And so this is just an example of how this is an example of the organization, self-organization of topological defects. And as I said at the beginning, that's a hierarchical process. So we can just round out our comments by mentioning that the connection to superconductivity later in the course we'll talk about what happens when you have a charged superfluid, which is what a superconductor is. And in that particular case, the analog of the vortex lattice is a magnetic lattice. When you put a magnetic field into a superconductor, it forms topological defects with magnetic flux going through them rather than angular momentum. And so basically rotating a neutral superfluid is analogous to applying a magnetic field to a charged superfluid. And that's what we call a superconductor. And basically, you can think of that as being, just because of the way that magnetic field causes electrons to rotate it, if you like. Both of these things generate vortices. So both generate quantum vortices. And but there's one difference. Which we'll get to when we talk about superconductors and the Anderson-Higgs mechanism. What happens is the B field is kind of like the omega field, I should say, in the superfluid, and the magnetic field decays as e to the minus r over lambda away from the vortex core. Rather than the velocity going as 1 over r in a superfluid. And so that means that the properties of the vortex lattice in a superconductor are slightly different than what happens in a superfluid, but the same thing is true. The last comment I want to make is that what happens if you have a turbulent superfluid? So I'm not going to say very much about this, but basically the idea is, let's suppose I've got some box. So here's a box like that with some surfaces like that. I can even make it three-dimensional and have periodic boundary conditions. But if I just put my fingers in and stir it around like this, there may be no net angular velocity, but locally there is angular velocity. And so what happens is you get vortex loops, like I'm drawing over here, something like this. So you get a tangled array of vortex loops. And they have to be loops because they can't just end in space because there's no sort of topological defect, which is at least for this system, which is just a point defect coupled to a line defect. So there are other superfluids where that can happen. That can even happen in some phases of helium-3. So that means then that if I've got a quantum vortex line, if it doesn't end on the walls of the container, like the top and bottom of a rotating bucket, then it just has to sort of go around and connect up to itself. And so you have to get it to have to get a loop. And then these things can have a very complicated dynamics, and depending on how they're stirred or how they are, or if they're left to decay, the time dependence can be worked out. And in the movie page, there's some pictures of this. Okay, so that's all I want to say for the moment about the topological defects. So what I want to move on to now is the next topic, which is the excitations of helium-2, in particular the idea of quasi-particles. So what I want, so that this section is really on helium-2, its main properties, but in particular the idea of quasi-particles. So what is that? What is our goal in this section? So we're going to cover a lot of ground here. So far we talked about the main novelty of emergent states when you have continuous symmetries that are broken, which is the topological defects. But we're also going to see that the low-lying excitations, that's a non-topological, underlying low-level excitations are also interesting. And what we mean by interesting is, in particular, that even though the basic system is interacting, even though the lowest level of description is strongly interacting, and that lowest level of description is just helium-4 atoms crashing into each other. Even though that's the case, there are excitations that behave as if they're non-interacting. And this is an extremely important concept in condensed matter physics at all scales, whether it be at the scale of quantum fields or nuclear matter or electronic matter or cold atoms. The idea that you can simplify a strongly interacting system into some effectively weakly interacting modes that, although they are weakly interacting, they have some phenomenological parameters which are controlled by the interactions themselves. So you don't get something for nothing. So the properties of these effectively non-interacting degrees of freedom are determined by the lower level degrees of freedom. And their interactions. So the idea here is you have some very complicated many-body system with many parameters, and then if you look at it at large enough length scales or small enough energies, then what you see is effectively non-interacting particles, and the properties of those non-interacting particles can be bundled up into some phenomenological constants, like an effective mass, for example, and those things can be calculated in principle from the many parameters that apply to the lower level degrees of freedom. So that's our goal, is to understand quasi-particles. And what we're going to do is we're going to do this in multiple ways. So one way to do this is phenomenologically. And by that, what we mean is we're going to guess what the excitation spectrum looks like. And relate that to thermodynamics. And that's what Landau did, and in fact won the Nobel Prize for. He showed how to do this, and so he was able to use essentially heat capacity data to figure out what was really going on inside a superfluid. And only many years later, when people could do neutron scattering and so on, were people able to verify that. So we'll talk about that in detail. We're also going to talk about the idea that we can calculate in the two fluid model. We're going to be able to calculate, say, the normal fluid density, which tells you about the quasi-particles. We're going to calculate that from the excitation spectrum. And that's something that you're going to do part of in homework. And then the other thing that we will do in this section is we will do a detailed calculation of weakly interacting bosons. So we're going to calculate and explicitly construct the quasi-particles. Using second quantization. And perturbation theory. So there's a lot of stuff here, but everything that we're going to learn in this section, it basically is what you do all the time in every condensed matter system. So let's talk about the excitation spectrum. So let's start with section 3.1. So let's first of all start off by defining what we actually mean by quasi-particles. So what is its sort of functional form? So what we're going to say is this: the basic idea is to say, I can think of the energy of the system can be written down as the energy of the ground state, and then I can create elementary excitations. So we're going to say that we create elementary excitations, and they will have some momentum, so we'll call that P. And how many of those excitations we'll have at some particular momentum P, we'll call that N of P. And then how much energy do they have, we'll call that epsilon of P. And that's what we mean by the excitation spectrum. So this obviously isn't a complete result, because there's no reason to believe that you can do this. And so that there's correction terms here, which I'm not going to write down at the moment. But those things describe the interactions between the quasi-particles. And what do we think that those interactions terms would be? Well, this term over here is the number of quasi-particles per unit volume. So if we just had this first term, that would just say that these things are like an ideal gas. And so what we'd expect is that if there's interactions between them, that those interactions are going to be proportional to a quadratic power of n. So this term over here would be a correction term, which is going to be proportional to n squared, and higher order terms, of course. So this is then the idea. So what this says is that this is like an ideal gas of quasi-particles, whatever they happen to be. And we don't really know what they are with this way we're describing these things, but these are quasi-particles whose energy spectrum, and sometimes I'll call this a dispersion relation, is epsilon of P. So our goal then is to actually find out what is epsilon of P. In other words, if we can do this, if this is possible, we need to figure out what epsilon of P has to be. And then this part over here is the actually, let me use a different color so you can clearly see it. So this part over here, so this is the ground state. And of course, the ground state is going to depend in some very complicated way on the interactions between the helium-4 atoms, or whatever are the degrees of freedom that are underlying. So the ground state is very complicated. Many body behavior of the underlying degrees of freedom. In this case, helium-4. And we can't expect to calculate that, because this in general, why is it very complicated? Well, it's very complicated because we have strong interactions. So that makes it hard. But what our hope is that by just focusing on the difference between the actual energy and the energy of the complicated many-body ground state, then we get something simple. So the idea is that this thing over here is these things are weakly interacting. And so that means that the physics of these is easy. And instead of asking what is going on for the whole system, we're just going to focus on the energy minus the thing that we can't compute, the actual ground state. So the basic trick is that if you're at low temperatures, the excitations above the ground state are very dilute. And so therefore weakly interacting, because they just scatter very occasionally. And so they're going to be weakly interacting, and because we are dealing with bosons, these are going to be weakly interacting bosons. So what did Landau do? So Landau had a great idea that if this is true, when you measure the heat capacity of a system, what you are measuring is the excitations above the ground state. And so Landau's idea was that when you measure heat capacity, what that is equal to is a measurement of the thermodynamics of the quasi-particles. Because what you're measuring are the properties as functions of temperature differences. And so what you are measuring then is the effect of just the quasi-particles. So in fact, what Landau was able to do, so Landau actually guessed in this way. The form of x epsilon of p from data on the heat capacity. And you know, so this was in like 1947, and then later his guess was confirmed. By neutron scattering, maybe 20 years later or something. Okay, so let's draw what this thing actually looks like. So here is going to be wave number in units of 10 to the 8 inverse centimeters. Up here, I'm going to plot epsilon of k divided by Boltzmann's constant. And the upper scale here, this is a number which is about 20. So this is 0, this is 1, 2, 3, something like that. And then what he discovered was this strange curve over here. So let's see if I can get it about right. Something like that. So it's quite a complicated form. You probably wouldn't have guessed it like that. So here at the origin, there's a linear part. So there's this linear part here. Epsilon is proportional to k. So it's a linear part. So that means that these things, we can think of these as being sound waves or phonons, propagating modes whose dispersion relation goes like k, so they're not diffusive. So those are called phonons. This thing over here is called the Roton minimum. And the idea was that these corresponded to some kind of quasi-particles. If these linear interspersion relations were just sound waves or phonons, then the idea was that these things might be related to rotations, vortices, or something like that. That's not, as far as I know, true, but the name has stuck. So they happen to be called rotons. Okay, so it's just so really we should think of this as just a name, and so in this part over here, at these turning points, the k by the epsilon goes to infinity at this turning point over here and at this turning point over here. Okay, so that's the form of the dispersion relation. So let's write it down. So epsilon of k in the phonons is just h bar times something times k, and this something is a coefficient that's called the speed of first sound. And then so that's the phonons. And then for the rotons, we just simply say that epsilon of k is equal to some gap. So we'll call this gap delta. This is delta over Boltzmann's constant. So this gap is delta plus, and then it's some sort of quadratic. So we'll say it's k minus some k naught squared over some effective mass to m star, like so. And this is a k0. Again, just so you know, the values of these parameters. So delta over kb, that's about 8.7 Kelvin. M star is about 0.16 times the mass of helium-4. K naught is about 1.9 times 10 to the 8 in centimeters. I've drawn this over here. It really should be over there. So sorry about that. And C1 is about 238 meters per second. So this is what happens. Now, as you go to higher and higher temperatures, you excite more and more of these modes. So when you're at low temperatures, and what low is obviously a lot less than 8 Kelvin. So at low temperatures, so let's say roughly order 1K or less, you only excite the phonons. And then above that, start to see the rotons. And above about 2K, what happens above 2K? Well, you get so many things excited that the idea that these quasi-particles are non-interacting breaks down. So above 2K, the non-interacting assumption is badly wrong. So the idea then that I want you to make sure you understand is that the quasi-particles are a low temperature phenomenon. So for example, think about the high temperature superconductors. It's not at all obvious that if you have a high temperature superconductor that you would get non-interacting quasi-particles, because they're at such high temperatures, say 90 Kelvin or 150 Kelvin or something like this, that you would not expect them to be non-interacting. And so there's a lot of, so that's a whole, I don't know, that's part of the mystery and complication of high temperature superconductivity. So let's now talk about the thermodynamics of these quasi-particles. So the first comment I want to make is that the phonons in helium-4 are not the same as sound waves in a gas. Actually, I've said that completely wrong. So let me take that back. They're not sound waves in a solid. Usually when you think about phonons and solid state physics, you think of just phonons and literally sound waves in a solid. And the reason for that is that in a solid you have longitudinal and transverse modes. And you can have transverse phonons in a solid because you have a static shear modulus. So this is not true in a fluid. So you can't support a shear, and so that means you only have a longitudinal mode. Okay, so then the other thing is that the next thing is that the quasi-particles are not conserved. They're not like the atoms, not the same as atoms. Okay, so what that means is that their free energy of the system cannot depend on the number of quasi-particles, which I'll call NQP. And so that means that the free energy with respect to n is equal to 0 because it doesn't depend on it, and dF by dN is what we mean by the chemical potential. So the point is that the chemical potential of the quasi-particles is not the same thing as the quasi-potential as the chemical potential of helium. So the chemical potential of liquid helium near t equals 0 is mu over Kb is about -7 degrees Kelvin, and so which is different, obviously different from 0. Okay, so the difference between these things is that the quasi-particles are not the same thing as atoms. And in general, as you'll see when we construct the quasi-particles using quantum field theory, quasi-particles are some kind of collective excitation of the condensate. And we're going to see that explicitly when we get there. Okay, so now let's just in the last few minutes let's try to write down some of the thermodynamics. So we know that they will obey their bosonic quasi-particles. So what I'm going to do is I'm going to write down the number of quasi-particles, So that's going to be the sum over wave number state or momenta k of the Bose-Einstein distribution function. And that's a function of energy minus mu. Mu is equal to 0, so it's just a function of energy. And this is what I can say is writing down the sum of n of k here, and the n of k number of quasi-particles at any given wave number is just 1 over e to the beta epsilon of k minus 1, just like that. So that's how we compute the total number of quasi-particles. And so I can write down the number of quasi-particles as a integral. V over 2 pi cubed is the density of states in k space of integral d3k n over k, like that. And then the partition function of the system is just the sum over states of e to minus beta e0 plus the sum over k n of k epsilon of k plus order n squared. So that's what we mean by the partition function. And then the free energy of the system is just F is equal to minus kBt log of z, and then I can write that as E naught plus kBtV times the integral d3k over 2 pi cubed times the log of 1 minus e to the minus beta epsilon of k. And so the point is that if I know that at low temperatures I only have to worry about the phonons, so then at low temperatures I can approximate epsilon like that, then I can compute the result, and I'm going to just do that, and then that'll be the end of today's lecture. So I can't calculate the ground state energy because that's something complicated in any body. So we'll call this the free energy of the phonons. And then I can just simply do the integral because it's just kBt v integral d3k over 2 pi cubed times the logarithm of 1 minus e to the minus beta h bar c1 absolute value of k, like that. And the way I can do the integral is by substituting x to be beta h bar c1 absolute value of k. And if I do that, then what I get is that f phonon is equal to kBtV, the integral from 0 to infinity 4 pi over 2 pi cubed. Now I'm just writing d3k as 4 pi k squared dk, so this ends up being x squared dx times the logarithm of 1 minus e to the minus x, and then divided by 1 over beta h bar c1 all cubed. And this integral is easy to do. You can just look it up. So the integral is just minus 2 pi to the 4th over 720. Some of you will know how to do that by Contour integration. And so finally what we end up with, and this is where we'll end today, is the free energy for phonons is just minus pi squared over 90 h bar C1 cubed times the volume of the system times kBt to the 4th power. So what that says is, if I know how the free energy varies with temperature, then I know how the heat capacity varies with temperature. And so from the way that the heat capacity varies with temperature, I can read off the speed of first sound. And indeed, if the heat capacity does vary, so the heat capacity should go as T cubed. And so you go and measure it and you see, excuse me, and you see that it does. And so that's how Landau was able to verify his guess and understand what the form of the excitation spectrum was. Okay, so we'll continue this on Wednesday. I'm going to stop the lecture, and then I'll be happy to take any questions.